Welcome to another podcast. This episode we're going to be taking a look at another Fourier transform example, this time how to solve Laplace's equation via the Fourier transform. So let me remind you of what Laplace's equation is. This is the second order Laplace's equation, or two-dimensional version. So uxx plus uyy equals 0. Here the variable x is ranging from minus infinity to infinity, and I'm thinking of the variable y as ranging from 0 to infinity. So I'm thinking of the upper half plane. Remember, Laplace's equation governs the steady state of the heat equation. So if I think about what is the long-term steady state distribution of heat in a infinitely large metal slab that covers the top half of the plane, then this would be the equation which governs that. We're going to talk more about those later in the semester, but this is the equation which governs that. So we need an initial condition here. So suppose that the initial temperature profile is f of x. And we also need some mathematical boundary conditions here. Particularly, we need the function u of xy to stay bounded as y goes to infinity. So as we increase going in the y direction, we need that to stay bounded. So we need boundedness as y increases. Since x ranges over negative infinity to infinity, that's going to be our transform variable here. So I'm going to be doing the transform with respect to x. So we'll begin by taking the Fourier transform of both sides of the equation. So the Fourier transform of the left-hand side using the linearity of the transform is given by this. Keep in mind this is with respect to x. So when I take the transform of uxx, I have a property that says that creates two copies of I omega minus I omega squared. And then we get u hat omega, so x transforms to omega, and y stays y, plus the Fourier transform of uyy. It's going to ignore the y derivatives. They just go outside the integral. And then the Fourier transform of 0 is 0. So this is the Fourier transform for this particular problem. And sorry, this should just be I omega, not minus I omega. So I omega squared, two copies of I omega. And so what we end up with here is a equation of the form uyy minus omega squared u equals 0. And because there's only one derivative in the problem, then I want to think of this as an ODE. Let me go ahead and do the boundary condition, or the initial condition as well. If I take the Fourier transform of the boundary condition u of x 0, the Fourier transform of that is u hat at omega 0, and that equals the Fourier transform of little f, which is capital F omega. So my new boundary value problem here is going to be uyy minus omega squared u hat equals 0, subject to the condition u hat omega 0 is f of omega. So this is the transformed boundary value problem. Actually, sorry, this would be an initial value problem, but it's got the boundary, the implicit boundary conditions. So this is the transformed initial value problem that we have to solve, and this problem is essentially an ODE. In other words, I can think of this kind of as I would think of this equation from ODE. So I just think of this as being u of omega equals f of omega, or excuse me, u of 0, because omega, y is the variable here, so it would be u of 0 equals f of omega. This is how I can think of it back in ODE. So this is the PDE version, but this is sort of the ODE version of this problem. And if I think about the ODE version of this problem and solve it, then since this is a second order differential equation, I can solve it using the characteristic equation. So r squared minus omega squared equals 0. So r is equal to plus or minus the square root of omega squared, which is plus or minus omega. And we only need one of those roots, we need both those roots. And essentially what that allows us to do then is express the solution here, which is a solution in terms of y as a constant times e to the omega y plus b e to the minus omega y. So that would be the ODE solution. Remember, we get the two roots plus or minus omega. So back over here with the PDE, we think of this as being the PDE solution now is u hat of omega y equals, and this constant a is constant with respect to y, which still means it can be a function of omega. So on the PDE side of things, we think of it as a omega, and then this is e to the omega y plus b of omega e to the minus omega y. And so this is my solution to that IVP. And now all I need to do is figure out what my coefficients a omega and b omega are. In order to do that, I have to apply this initial condition. So in doing so, I'm basically looking at u hat of omega 0, which is a omega, e to the 0, which is 1, plus b omega. Now, we have these other properties that this thing has to hold, and this is very important here, that we need this to hold as y goes to infinity, which means I need a omega. So if you think about this property in relationship to this, because a omega is the coefficient of e to the omega y, as y goes to infinity, then I need a omega to go to 0. Basically, a omega needs to equal 0 when omega is greater than 0, and b of omega needs to equal 0 when omega is less than 0. The best way to write that then is to say that this function u of omega, u hat of omega, is essentially just c of omega times, rather than write it e to the omega y, e to the minus omega y, since these two things have to satisfy this, I might as well write it as e to the minus absolute value of omega y, because it depends on when omega is greater than 0 or less than 0. So while this is the solution involving two constants a and b, the boundary condition that we've imposed here implies that we really only need one constant in the problem. And it's a good thing, because we were out of luck here because we had two constants and only one equation. But when you add this to the picture, it really reduces to having only one constant in the problem. And we can solve for that constant by now reapplying the same boundary condition with y equal to 0, which is c omega when y is 0, and that has to equal f of omega by the condition. So our solution here to u hat is u hat of omega y is f of omega times e to the minus omega y. And we can get a solution here if we can take the inverse transform. So can I take the inverse transform of each side? That becomes the question. Well, the inverse transform of the left-hand side is regular u. Omega gets transformed back to x, y stays the same. Here we're taking the inverse transform of a product of two functions of omega, so we know with the convolution property that we can split them across convolution, or basically convolve them. And so we are looking at this product, or this convolution product. And so we can do this problem as long as the inverse transform of capital F is little f, as long as we know what the inverse transform of this is. Now, I'm going to create a little bit of room here in order to do this. But that's going to be our next assignment, is trying to figure out what that is. So remember the definition of the inverse transform here. So if I'm looking at the inverse transform of e to the minus omega y, that is equal to 1 over 2 pi integral from minus infinity to infinity of e to the minus omega y e to the I omega x d omega. So this is our definition of the inverse transform. Now, this is one of these transforms that we should know, but we haven't really talked about it in class, so I wanted to go ahead and show you the work for it. Because the absolute value is involved here, remember the definition of the absolute value of omega would be that omega it's just omega when omega is greater than 0, and it's negative omega when omega is less than 0. That definition inspires us to break this up into two integrals. So the first integral is the integral from 0 to infinity, where the absolute value of omega gets replaced with just omega. And the second integral is the integral from minus infinity to 0, where it gets replaced with negative omega. Now, if we simplify this, each side, then basically what we'll end up with on this side is the integral from 0 to infinity of e to the minus, I'm going to pull out an omega, and we have a y minus ix. And here we have the opposite. If we pull out an omega here, if we pull out a negative omega here, we have negative y minus ix. And so now if we try to integrate these, if I integrate the first one, then if you think about what the antiderivative looks like for this, it's of the form e to the minus omega y minus ix over, I'm looking at the coefficient here, which is negative y minus ix, the coefficient of omega, and I'm going to evaluate that from 0 to infinity. Then I'm going to do the same thing over here, but it's slightly different here. Chain rules is slightly different. So the chain rule on this side would be minus y minus ix, evaluated from minus infinity to 0. Okay, so there's a lot of work that's taking place there. So once again, I'm going to create some more space up here to finish this problem out. I want to make sure I leave sort of the conclusion that we're at this point. I just need to fill in this thing. What is its inverse transform? So continuing with that line, we have 1 over 2 pi. And then if I look at the first piece, I know at infinity, this thing is gonna die because it's a decaying exponential. So I know at infinity, this particular piece is going to go to 0. And then when I plug 0 in for omega, I'm going to get the top to be 1, and then I've got the bottom, because it's a negative, I get this negative to cancel. So this piece will end up as y minus ix when I evaluate it. Similarly over here, I end up with 0 being the first thing I plug in. So because the negative infinity is going to cancel out over here, notice that I can pull the negative out here and make this a positive omega. So this is actually an increasing. So as it goes to negative infinity, it goes to 0. I can actually plug in the 0 now for the first part, and because this is a negative here with the negative inside, I end up, when I evaluating it, getting y plus ix. So that works out really nicely, because what you end up with here is, if I get a common denominator inside there, I end up with y plus ix plus y minus ix, and when I square those two, I just am squaring, I get the conjugate basically. I'm taking the conjugate of each of those, so multiplying them together, I just get the squares of y and x. And what ends up happening here is the top cancels out very nicely, so that we get 2y over y squared plus x squared, which is just, in this particular case, it's just 1 over pi times y over y squared plus x squared. And so what we've discovered here is the inverse transform of this term is 1 over pi y over y squared plus x squared. Now, what's really interesting about all of this is very special in mathematics, this particular function. It's called the Poisson kernel. So you know how we had the Dirichlet kernel for the heat equation, which sort of controlled how the heat equation functioned. Here we have something called the Poisson kernel, which is going to control how Laplace's equation will function and spread out heat. It's related to something called the maximum principle that we'll talk about later in the semester, but I just wanted to give you another example of the Fourier transform to look at. Particularly what's different about this one and what you should focus on is the impact of this mathematical boundary condition, what it made on taking what did have a problem with two constants, if you recall, and transforming it down to one with only one. So that was the big innovation, or the big differentiation of this problem from what we did with the heat equation. All right, thank you for watching.